Good morning, all. This is a project with project on oscillatory behavior of simple kinetic model for proteolysis during cell invasion. So this was jointly done by myself, Surya Silvarajan, and Jeff Coulter. So this was a paper which was published in Biophysical Journal in 1999. So the idea of this particular paper was to understand how cell invasion happens uh, in a highly organized manner, both in time and space. When the cell tries to invade into the extracellular matrix, which happens during embryogenesis and cancer. And why is this an important paper? Because this topic started gaining its importance both experimentally and theoretically. People try to model the experiments during the late 2000s, where they tried developing a minimalistic model which explains the oscillatory behavior, which initially happens before the cell decides between staying in the same extracellular matrix or deciding between invasion. So these are the two different possible paths the cell can take. So the minimal model which was proposed in this particular paper was about a cell having two different uh, pathways. One is a counterclockwise pathway, and the other one is a clockwise pathway. And the tug of war between these two pathways decides whether the cell takes the stage of cell division, cell invasion, or stays put in where it starts off. So there is this enzyme E, which is a proteinase enzyme, which is also released in the extracellular matrix, which is produced within the cell. And this could either interact with the extracellular matrix, ECM, protein, which is a fibronectin protein in this case. It can either undergo uh, a degradation of the extracellular matrix to produce a proteolytic fragment L, or it could also just combine with the enzyme and form an RS complex, which serves as a feedback back to the cell. So the two different parameters, alpha and beta, decides which of these pathways become more relevant in the long run. And Michaelis-Menten forms the heart of this model, where you have the enzyme substrate complex reacting to give rise to product and back and the enzyme back. Yes, so the background for this particular paper, so the cells have this particular enzyme called as a matrix metalloproteinases, which is the actual proteinase present in the cell, which can degrade the extracellular matrix, and this degradation leads to uh, loss of the basement membrane and hen- and helps the cell invade into the extracellular matrix. So the mathematical model present in the Berry's paper involves a set of linear ordinary differential equations, and there are six of them. So each of them has a production term and a degradation term. For instance, the first equation, which is the rate of change of S, has the proteolysis term and integration binding term. And similarly, each of the differential equations for L and ES and DL and RL and RS similarly has an uh, production term and a degradation term. The total receptor concentration is equal to the receptor plus the RL plus RS. So all of this has been worked out in the framework of linear differential equations and not the classical nonlinear case of the Hills function, which is used in modeling Michaelis-Menten equations. So one important point to be noted is the enzyme rate of neosynthesis has been put in as in a change of RS into time into alpha plus beta into rate of change of RL, which is pretty different from most of the neosynthesis term used in other papers. So the simulation So we tried implementing the differential equations presented in the paper. So initially, the idea was to implement all of the results in the paper and to see if we are able to reproduce a paper. But as we started implementing it, and also from Dr. Emilis, who had provided some feedback on what is the on why the paper didn't get the right results. It was primarily because we realized they were working in the regime where the uh, the simulations were running in the regime of the numerical errors. It was well beyond the precision beyond which the computer could run the simulations perfectly. So there were numerical errors which actually led to oscillations, and it was not actually an true oscillation which was actually presented in the paper. So we started off setting up the task one in terms of the actual differential equations and the values which were taken from the paper directly. So all of this different parameters were actually taken from the paper, and we realized we could actually get an oscillation, but the concentration plot, which was the very first plot which was there in the paper, the concentration of RL and RS with respect to time tends to show an oscillation, but we realized the concentration was negative. So the concentration being negative was against one of the physical laws, as the concentration couldn't be negative. And the reason we realized was it was all working in the regime where the numerical precision was well beyond which the computer could handle. And it was not the true case of oscillation. And we would present the next few tasks, which would be related to when exactly to expect a true oscillation, and how and when can we expect numerical errors in here.
Okay.
So hereafter, Jeff will take over. Thank you.
So we want to see kind of gain some insight into where the issue might be coming from and why we're getting these negative concentrations. It could be something from poor parameters to, as we'll show, that the model simply can't oscillate. And so how we do this is we apply linear stability analysis, since the paper's model has 6 equations and therefore gives us a 6-dimensional problem. We're kind of walking through the steps with this simpler 2-dimensional model of a spring with potentially damped or driven dynamics given by this equation, and then converted into 2 coupled first order equations. So we go through setting up the matrix vector version of this system, and then we talk about how the eigenvalues and eigenvectors and consequently the trace and determinant of this matrix here can give us a qualitative insight into system dynamics. We talk about how there's no physical reason that the eigenvalues have to be real, they can be complex. And we look at how the complex nature of the eigenvalues can give rise to oscillations or orbits in phase space, and how the sign of the trace of the matrix determines whether these oscillations will form a sink or source, or maybe just a closed loop. So after this, we have some plots showing how beta, which is equivalent to the trace in this system, lead to different dynamics. Here, the red dots and the damped and driven simulations represent the initial conditions or starting point. So we see that damped oscillations curl into a fixed point, whereas driven oscillations start at a point and grow without bound. So following this, since the model from the paper is nonlinear, we go into how you can approximate these nonlinear equations as a system of linear equations by using Taylor series. We discuss how we want to expand these functions around the equilibrium points and how you can find the equilibrium points. We then go through expanding the functions in quite a bit of detail and show how we can achieve from this a matrix vector equation very similar to the linear case. However, now instead of the linear transformation matrix, we have this matrix of derivatives, which is known as the Jacobian matrix. So now getting into task 2, we want to introduce the user to the SymPy Python package, which is used to symbolically manipulate equations. This task will, all of this code will be absent from the unfinished notebook, and it will be up to the user to go through some of the SymPy documentation and find some of these functions that will be needed. There are only 3 or so. It's not that difficult, I think, and it's something that's useful for something that's useful if you want to write code. It's looking through documentation. So briefly, this first line specifies that these variables are symbols. These lines express the differential equations in their symbolic form. These set the equation equal to 0. And then this solves for the stationary points. Following this is noted above, we want to find the Jacobian matrix because that's what relates the time derivatives to the variables themselves. So again, this Jacobian matrix will be absent in the final implementation. I will leave this here just because it's useful for printing, but the user will have to use the SymPy differentiation function to compute the Jacobian matrix. Following this, they will evaluate the Jacobian at the stationary points that they found in task 2. And they will then compute the determinant, which is explained in some of the text above is necessary. You don't want it to be 0 if you want oscillations, because when it's 0, that implies either a line or plane of fixed points in phase space, which will lead the which will prevent the dynamics from oscillating. And so we see that in our case, we have a determinant equal to 0, which implies that the system cannot oscillate. Following this, we go into how the current parameter values of the system, some of them achieve values proportional to 10 to the negative 17. However, if you look at the machine epsilon, then you'll find that this value is too small, and the computer is not able to computationally work with these values. So by scaling up in task 4, you will see that the oscillations do go away. And for this task, the user will have to take really the initial conditions as well as these and convert them all to scale them up to some degree. I think we specify the nanomolar and then make a plot similar to task 1. So this was the last task for this notebook.